Have you ever wondered what the difference between a mineral and a rock is? Well, did you know ice is actually a mineral? In this video, we'll find out what a mineral is and how it's different from a rock. In addition, we'll also go into some basic techniques to identify common minerals. So what exactly is a mineral? And how is ice one? Well, a mineral is defined as a naturally occurring, inorganic, crystalline solid with a defined but variable chemical formula. While a rock is naturally made of one or more minerals and are generally grouped into three types: igneous rocks, which are cooled from a melt; sedimentary rocks, which are either broken bits of rocks that are recompacted together through a process known as diagenesis, or precipitated from a solution; while metamorphic rocks are previous rocks that undergo heating and pressure, transforming them into different rocks, which is known as metamorphosis. So let's go over that mineral definition. Minerals are naturally occurring in that they form in nature without human intervention. Though we can replicate many of these conditions in the lab, such as lab-grown diamonds, which are identical to the natural type. So nowadays, there's a blur between these. Minerals must also be inorganic. They can't be organic, that is, no hydrogen to carbon bonds allowed. Otherwise, we'd just be doing organic chemistry. Minerals must be solids. That's the state of matter. Pretty straightforward. Minerals are crystalline. This just means that the atoms that make up the mineral are arranged in a specific pattern known as a lattice. And there are 7 crystal systems minerals can form in, which depends on the shape of the unit cell, which is formed by the lattice. Though sometimes rhombohedral is lumped in with hexagonal, leaving 6 crystal systems. Minerals also have a defined but variable chemical composition. This means they are generally formed from the same elements each time, though some elements in the structure may be substituted for others. For example, the mineral olivine has a composition of 2 magnesium or iron and 1 silicon and 4 oxygen. Magnesium, iron 2, silicon, oxygen 4. This is because it can incorporate either magnesium or iron into its structure depending on what is available in the magma. This is called solid solution, and both pure compositions, known as end members, have their own mineral names. The magnesium end member is called forsterite, and the iron end member is called fayalite. So now that we know what a mineral is, how is ice one? Well, ice checks all the requirements. Ice does naturally occur, think snow or glaciers. Ice is H2O, so no hydrogen-carbon bonds, and as such is inorganic. Ice is a solid, the solid state of water, and ice has a defined chemical structure, H2O. And finally, ice is crystalline. It's most commonly formed in the hexagonal system. So yes, ice is a mineral. Okay, but there are so many minerals. How can we determine which mineral we have? Well, there are a few properties we can examine to identify a mineral in a hand sample. Let's go over them. Let's start with the most obvious, the color of a mineral. Minerals come in all varieties of color, but it's generally not the most diagnostic property. It can be useful along with other properties, or used for really similar minerals. For example, biotite and muscovite are quite similar mica minerals, but biotite is dark while muscovite is clear, so color is an important diagnostic property. But don't just rely on color, as many minerals come in many colors, and trace elements can alter the color as well. Next, we'll look at lustre. Lustre defines the way light interacts with the surface of a mineral, kind of like the texture the surface appears to have. Examples include metallic, like this pyrite, vitreous, like this quartz, or pearly, like this biotite. There are a bunch of other ways you can describe the lustre as well, such as earthy or dull. Next, we'll look at the crystal forms and crystal habits. This describes the general shape of the mineral. Minerals can come in a variety of forms, such as this cubic pyrite, this platy biotite, this prismatic quartz, and a bunch of others, as you can see here. In crystallography, we go into more specifics of the crystal shape. If you want to see some crystallography videos, comment below and subscribe. Next, we'll look at mineral hardness. Hardness is defined by the strength of the crystal lattice, and we can test it by whether items with a known hardness can scratch them. To do this, we use the Mohs hardness scale, which is a relative scale that goes from the soft talc with a hardness of 1 to diamond with a hardness of 10. There are also common items we can score on the scale. Copper pennies are roughly 3.5, glass is roughly 5.5, and steel nails are roughly 6.5. And we can attempt to scratch our specimen with one of these to estimate its hardness. Next, we'll look at the streak of a mineral. Many minerals have a different color when ground into dust than they do when whole. To test this, we could grind our specimen into dust, but it wouldn't be very helpful to destroy our specimen. Instead, we use a streak plate, which is just an unglazed bit of ceramic. You just take your mineral and rub it along the streak plate, and the streak left behind is just powdered mineral. The only caveat is that the plate only has a hardness of roughly 7, so anything at or higher than 7 hardness will just scratch the plate. As you can see, this pyrite, or fool's gold, which starts off with a brassy color, ends up having a black streak, revealing its iron composition. Next, we'll look at the mineral's specific gravity. Specific gravity is just the density of a mineral relative to water, as denoted by this equation. But we don't really need to calculate this in the field. Generally, you can just estimate it based on how heavy a mineral feels. For example, this pyrite is roughly the same size as this biotite, but the pyrite feels much heavier since it's denser. Next, we'll look at both cleavage and fracture. These two properties determine how a mineral breaks. You don't necessarily need to break it yourself, as most specimens already show some wear or previous breaks. Fractures are any rough surface breaks, and generally aren't super diagnostic, except in certain cases such as the mineral quartz, or the mineraloid obsidian, which both show conchoidal fracture, which are these kind of round breakpoints, like glass. And yes, obsidian is not a mineral, as it lacks a crystal lattice. Instead, it's just an amorphous lump of volcanic glass, so we call it a mineraloid instead. On the other hand, cleavage is an incredibly important diagnostic property that results from planes of weakness in the mineral's structure. These are generally smoother, clean breaks that repeat in patterns throughout the crystal, and are due to weaknesses in the atomic structure of the mineral. A given mineral may have one or multiple cleavage planes throughout, though not all minerals have a cleavage plane. And we describe them as either poor, good, or perfect, based on how clean the cut is. In addition to denoting the angle between multiple cleavage planes. For example, biotite has a single perfect cleavage, which forms the platy habit. We describe this as perfect cleavage at 180 degrees. While feldspars have 2 good cleavages that meet at roughly 90 degrees, as you can see here. And halite, which is common table salt, has 3 perfect cleavages at 90 degrees, also known as perfect cubic cleavage. Some minerals have poor cleavage, such as those of olivine, but these are rarely noticeable, so mostly ignored. While some minerals, such as quartz or magnetite, have no cleavage. And some minerals are almost impossible to identify without looking at cleavage, such as hornblende, a variety of amphibole, with cleavages at 124 and 56 degrees, and pyroxene, with nearly 90-degree cleavages, that otherwise look very similar in hand samples. There are other minor properties used to distinguish minerals, but these are mostly specific cases. Magnetism can be used to identify ferrous minerals. Taste can be used to identify halite, though I don't recommend licking random rocks. Effervescence, or fizzing when exposed to HCl, is used to identify calcite, which always fizzes, and dolomite, which only fizzes when powdered. And that's the majority of mineral properties. Color, luster, habit, hardness, streak, specific gravity, fracture, cleavage, and some other minor ones. However, this isn't always enough to identify similar minerals, such as clinopyroxene and orthopyroxene, so we'll need to dig a little deeper. In fact, I already made a video on the next step, identifying minerals in thin section. You can access that video at the top left here. And if you enjoyed this video, make sure to like, share, subscribe, and comment. Then maybe hit one of these videos.